Stop scrolling. In the last episode, we were left with a paradox: a global scoreboard with no referee. How can millions of anonymous participants agree on who owns what without a central authority to enforce the rules? For anyone who thinks in systems, this is the fundamental problem. For decades, every attempt to create digital money failed to solve it. They left a graveyard of broken currencies because no one could engineer agreement among strangers who had every incentive to cheat. The solution, when it finally arrived, was not a complex legal framework or a moral plea. It was a single, brutally simple economic rule. A rule that doesn't fight human nature, but channels it. It took the most chaotic force in the universe, rational self-interest, and turned it into the network's greatest source of security. Today, we are moving beyond the history and into the machine itself. We will explain the engine of proof of work, not with hype, but with precision. Understanding this mechanism will change how you view not just money, but the nature of trust and coordination itself. For years, the brightest minds in cryptography tried to create digital cash. Projects like DigiCash, eGold, and BitGold all solved pieces of the puzzle, but each collapsed because it relied on a central referee. The double spending problem, the ability to copy and paste digital money, was a fatal flaw. Without a trusted arbiter, there could be no agreement. Money requires a single source of truth, but the internet is a network of strangers. How do you reconcile the two? The answer is not about technology alone. It is about the specific, unbreakable economic rule that makes the Bitcoin network so profoundly resilient. To appreciate the elegance of Bitcoin's design, we must first walk through the ruins of what came before. The dream of private digital money is not new. It began in the early days of the internet with a series of brilliant but fatally flawed experiments. First was DigiCash, created by cryptographer David Chaum. His invention, eCash, used blind signatures to enable anonymous transactions, a level of privacy many modern systems still haven't achieved. It was revolutionary, attracting interest from major banks and even Microsoft. But eCash had a central point of failure. The entire system was operated by one company, DigiCash Inc. When the company went bankrupt in 1998, eCash ceased to exist. The lesson was clear: central control creates systemic vulnerability. Next came eGold in 1996. It used a different model, backing its digital currency with physical gold held in a vault. It grew to millions of users, proving the immense global demand for a borderless currency outside the traditional banking system. Yet again, centralization was its undoing. The company operated as an unlicensed money transmitter, and when it faced legal action from the US government, its assets were seized and the system was shut down. Other attempts, like Hashcash and Nick Szabo's BitGold, introduced concepts like proof of work and digital scarcity. Each solved a piece of the puzzle. DigiCash gave us privacy, eGold demonstrated global demand, and BitGold sketched the blueprint for scarcity. But none could solve what Satoshi Nakamoto would call the double spending problem. In the physical world, double spending is impossible. If you hand someone a $20 bill, you no longer possess it. But in the digital realm, anything can be copied. What stops a user from sending the same digital coin to two different people simultaneously? In the traditional financial system, the answer is a trusted third party. Visa or your bank acts as the referee, maintaining a private ledger and settling transactions. The system works, but it comes at the cost of fees, potential censorship, and the requirement of absolute trust in those institutions. The early digital currencies could not escape this model. DigiCash was the referee. eGold was the referee. They were fragile because they could be shut down, regulated, or bankrupted. This was the great paradox. A truly decentralized currency requires thousands of computers to agree on a single transaction history. But without a leader to declare what is true, how could consensus ever be reached? Then, in 2008, a paper titled Bitcoin, a peer-to-peer electronic cash system, quietly appeared on a cryptography mailing list. It proposed a solution that was counterintuitive and elegant. It didn't try to eliminate greed or enforce honesty. Instead, it designed a system where acting honestly was simply the most profitable strategy. Satoshi Nakamoto's solution was not a new form of cryptography, but a masterful application of game theory disguised as a computer science problem. It is called proof of work. It works by making the right to update the official record costly, while making the reward for doing so honestly extremely valuable. Let's break down the mechanics. Imagine the Bitcoin network as a global public ledger, the blockchain. Tens of thousands of copies of this ledger exist on computers, or nodes, worldwide. This redundancy is the first layer of security. There is no central server to attack. Approximately every 10 minutes, a new block of transactions must be added to this ledger. The critical question is, who gets to add the next block? And how can everyone be certain that the information within it is valid? This is where a specialized group of network participants, known as miners, compete. Their competition is not a race to solve a complex math problem, but a brute force contest of chance. Think of it like a global lottery. To enter, a miner's computer must perform a specific task. Bundle the new transaction data, add a random number, and process it through a cryptographic function called SHA-256. This function produces a unique digital fingerprint, or a hash. The goal is to be the first to find a random number that generates a hash with a very specific, improbable feature. For instance, one that starts with a long string of zeros. There is no shortcut. The only way to find it is to guess, over and over, trillions of times per second. This computational effort is the work in proof of work. It requires specialized hardware and consumes a significant amount of electricity. That energy expenditure is not a flaw. It is the core of the security model, anchoring the digital ledger to the physical world through a real-world cost. The winner of this lottery, the first miner to find the correct hash, earns the right to broadcast their new block to the network. For this service, they receive a reward, a disbursement of new Bitcoin, known as the block subsidy, plus all the transaction fees from that block. After the 2024 halving, that subsidy is 3.125 BTC per block. This is the simple economic rule that drives the system. The cost of participation is real-world electricity. The prize is new Bitcoin. This structure elegantly solves the problem of trust. When a winning miner broadcasts their block, every other node on the network independently verifies it. This verification is the opposite of mining. It is computationally trivial. Nodes check two things. Are all transactions in the block valid? And does the block's hash prove that the required computational work was actually performed? If the block is valid, all nodes add it to their copy of the ledger, and the competition for the next block begins. If the block is invalid, for example, if the miner tried to award themselves more Bitcoin than permitted, the network nodes simply reject it. The miner's investment in electricity is completely wasted. Dishonesty is met with economic penalty. The system runs on verification, not trust. The mantra is, don't trust, verify. Miners adhere to the rules because it is the only way to get paid. Honesty is not a moral choice. It is enforced by the logic of profit and loss. But what if two miners find a valid block at roughly the same time? The protocol has a simple tiebreaker, the longest chain rule. The network will always recognize the version of the ledger that has the most cumulative computational work, the most energy, invested in it. Any miner who chooses to build upon a shorter chain is abandoning the consensus of the network, ensuring their work will be orphaned and their potential reward lost. They are choosing isolation from the only ledger the market recognizes. Competition decentralizes power. Energy cost makes cheating expensive. The block reward pays for the network's own security. The system aligns the rational self-interest of individual miners with the integrity of the entire network, producing a secure and trustworthy record without any central coordination. The power of this economic rule extends beyond its operational function. It is the source of the network's resilience. First, Bitcoin has no single point of failure. With systems like eGold or DigiCash, a single legal or technical failure could destroy the network. Bitcoin has no CEO, no headquarters, and no central server. Its ledger is replicated across tens of thousands of computers globally, secured by a competitive market of miners in different jurisdictions. To stop Bitcoin, one would have to shut down every miner everywhere simultaneously. The most frequently cited attack vector is the 51% attack. What if a single entity could control a majority of the network's total computing power? In theory, they could rewrite recent transaction history. For example, they could send Bitcoin to an exchange, sell it for fiat currency, and then use their majority power to create a new version of the blockchain where the initial transaction never occurred, allowing them to spend the same coins again. However, theoretical possibility is not the same as practical or economic feasibility. This is where the game theory becomes Bitcoin's primary defense. First, consider the acquisition cost. To gain 51% of Bitcoin's hash rate would require an immense capital investment in specialized mining hardware, costing many billions of dollars. Second, the operational cost. The electricity required to run this hardware would be staggering, comparable to the energy consumption of a small country. This represents a massive ongoing expense. Most importantly, consider the economic outcome. If an attacker spends these billions and successfully executes a double spend, the global market would witness the attack in real time. Confidence in Bitcoin's integrity would be severely damaged, and its price would likely collapse. The attacker, having spent a fortune to gain control of the network, would have succeeded only in destroying the value of the very asset they intended to steal. They would be the ruler of a worthless kingdom. For any rational economic actor, a 51% attack is a form of financial self-destruction. The cost to mount the attack far exceeds any potential gain. This is why, in its history, the Bitcoin network has never had a successful 51% attack. Smaller cryptocurrencies have been vulnerable because the cost to attack them is comparatively low. Bitcoin's massive and growing hash rate serves as an economic fortress. Its security scales with its value, creating a powerful, self-reinforcing feedback loop. This is what makes Bitcoin anti-fragile. It doesn't just withstand shocks. Its continued operation through them strengthens its credibility. Every time the network weathers a market crash or a regulatory challenge, the fact that it continues to produce blocks every 10 minutes serves as further proof of its resilience. It demonstrates that the core economic incentive holds. This core principle, replacing institutional trust with verifiable economic incentives, is the breakthrough. But this reliance on anonymous, self-interested actors points back to the system's greatest mystery. In the last episode, we asked how to build a scoreboard without a referee. Now we must ask, why would the architect of such a system design themselves to be completely irrelevant? Our next video will explore the identity and motivations of Satoshi Nakamoto. Understanding the founder's disappearance is critical to understanding the logic of the system itself. This is one of those ideas that's easier to understand by walking someone through it. If you found this explanation valuable, consider sharing it. So, what is the rule that makes Bitcoin so resilient? It is the radical idea that a system of predictable order can be built from chaotic self-interest. It is the discovery that you don't need to trust people if you make it profitable for them to behave in a trustworthy manner. Proof of work is not just an algorithm. It's an engine that converts the raw energy of economic calculation into the immutable record of digital truth. For decades, we relied on centralized institutions to serve as arbiters of truth. Bitcoin presented an alternative model. It demonstrated that truth does not have to be handed down from an authority. It can emerge from the bottom up, built by a network of competing peers, held in equilibrium by the ruthless logic of economics. The system is impartial. It does not care about identity, location, or belief. It only asks for proof of work. This is why Bitcoin has no single point of failure. It is a financial organism that has distributed not just its infrastructure, but its very incentive to survive. It is a network that pays for its own protection and has continued to operate uninterrupted, proving its design every 10 minutes, block by block. Bitcoin's resilience comes not from code, but from a perfectly balanced economic game where cooperation becomes the most rational, selfish choice. The scoreboard finally works, because the players now enforce the score themselves.